All right, we'll go ahead and begin the presentation. Again, today we're going to talk about the basics of LTE and some of the LTE measurements you can make with the base station analyzer. That actually applies to the 745 or 785 or the 748 or 788. All of these otherwise have signal analysis as part of the product line and what they support. That's otherwise shown here on this chart. This is part of the product family of the CellAdvisor. All of these also include RF over CPRI, and if you have a software license, you can even do signal analysis of the BBU of protocol that otherwise drives remote radio head. My personal interest is on just looking at the output of the transmitter, because if the output of the transmitter is good, there's really no reason to look at the CPRI interface, because you can pretty much assume that that is also okay. As far as the product family, you can see the 746 does leave out signal analysis. Again, some people opt to only go with a partial configuration. Fortunately for those at Ericsson, you have, I believe, 785Bs. Congratulations, that's pretty much top of the line of what we offer. And it's the multi-purpose. I'd also like to give you a bit of my perspective. My perspective as a test engineer of over 30 years. My three favorite words have always been control your environment. Somebody from marketing was kind enough to actually fill in a blank. And I now have actually two fill-in-the-blanks that I typically address as both RF as well as fiber. As a test engineer, there's two types of faults as far as phases. There's detection, and your goal is oftentimes 100%, wanting to know where all your weaknesses are at, whether they be functional problems, which are generally a lot easier to identify, or performance. And with failure types of performance, oftentimes you have to be very intimate with understanding dynamic range. Dynamic range can be anywhere from the noise floor to the point of saturation. And if you don't understand dynamic range of either the device under test or system under test or the test instrument, oftentimes you can get, when you say, unexpected results or results that otherwise are not representative of what you expect from that device under test. Ultimately, the highest cost is basically in terms of fault isolation. This is where efficiency, having test points, can oftentimes greatly increase your yield. As far as elements of testability, it doesn't matter if it's RF, fiber, audio, power, or otherwise. There are always three components when it comes to testability. First is access. These are test points. This is actually part of the control your environment. Yes, you can measure RF over the air, but if you're going to do that, understand that you have a number of factors that can otherwise weigh in to trying to make measurements over the air. And if you try to go back to an equipment manufacturer like Ericsson, aka Nokia, Siemens, or Ericsson, they're basically going to tell you or ask, how did you actually test that? And generally, they want to hear that you did it through a hardwired connection. Second point is visibility. Visibility can come from built-in tests, but more often than not, you get much greater visibility when you actually use external test equipment. And the third part of testability is controlling the device under test. Controlling the device under test is similar to testing your radio or your stereo. You're oftentimes going to turn down the audio, listen to the audio quality at a low volume, make sure there's no hum, static, crack, pop, and then turn up the volume and see what it sounds like. Well, the same thing should also be applied to many of your transmitters. You should have the ability to use OCNS or AILG. These are test modes of your transmitter that otherwise allow you to push it to full power, to look at signal quality or to look at possibly pin issues that otherwise could affect your receive. Otherwise, I just point out the aspects that can will affect RF quality. These can obviously be broken down into much finer points. But again, this is my perspective of where I come from when I otherwise try to present along the topics of test, especially RF. As far as the ports, let's start with the top. The primary port you're going to be using is a spectrum analyzer input for signal analysis. Like I said, you can also do signal analysis through the CPRI port if you have those licenses. But I also want to point out that there's a GPS port. I highly recommend the use of that GPS port, even in times where you think you may not be able to get GPS reception. The reason for that, please do not underestimate the capability of our GPS chipset that we've integrated into our product. Oftentimes, I mean very often, I will uncoil that GPS cord that's actually a coax. So I take out the inductive properties and keep the floor away from other sources of electronics, meaning laptops, power supplies, projectors, even our test equipment. And I have been amazed how many times I've otherwise gotten GPS reception in rooms with no windows. So please take advantage of that. But more importantly, what happens is the more you use that GPS antenna with the instrument, it actually serves to automatically calibrate the OCXO, the oven controlled crystal oscillator. This means that frequency error problems can be clearly seen when you have an atomic clock as your reference. And the more you use that GPS antenna with this instrument, the better it will remain calibrated to match GPS timing, which is the most accurate timing source that you can otherwise have. So again, I make it a habit of every time I set up the instrument, I do use a GPS port. On the front of the panel, you'll see that I actually have 5 buttons highlighted. I like to refer to these 5 buttons as my 5 favorites. Not that I don't use every button on the instrument, but I can pretty well assure you that every time you go to use the instrument, odds are extremely high that you'll have to touch at least each one of those buttons at least once. The mode basically shows you at the top here. You can already see what mode you're in, and that's basically the button that you would use to go to the top level of the instrument. Now please save yourself some time. If you're already in the mode that you need, you don't need to keep re-entering the mode because it has to reload the measurement, which is oftentimes a waste of time. More importantly is if you're in the mode that you want to be in, like LTE, FTD, signal analysis, and you want to get to the measurements, which is part of the center display that's highlighted here, the measurement indicator, please use the measure button on the numeric keypad. That measure button, or actually any button that's otherwise sharing the numeric keypad, the key to understanding how to use this is looking at the display. Notice this long area just above the main display, black highlighted area, that matches the background. This means that when you press any one of the numeric keypads, you're not going to get the numbers, you're going to get the words that are on those keypads. If it's highlighted like blue, it means that it is in fact a numeric keypad. You can use either the escape or the previous button to otherwise clear that to get back to the words that are on the buttons. Now, frequency, amplitude. These 2 buttons should be fairly obvious. Frequency to navigate the spectrum. If you don't know where your spectrum's at, it's going to be very difficult for you to maintain your spectrum or your signals when you're going to investigate them. So that should be fairly obvious. The amplitude scale, I highlight that. I probably say that's probably one of my most favorite of all 5 buttons, in large part because with a test instrument, and it comes to dynamic range, it's going to be through the amplitude scale that I turn on my preamp for weak signals, or I add attenuation, especially when I'm using a hardwired connection that may still be overdriving my instrument. It also serves to expand my scale so I can have greater visibility into what I'm seeing. So please make sure that you use the amplitude scale button as much as possible so that you have the greatest level of visibility. The 5th button here, and this is one you can ill afford to forget. This is known as the measure setup. What this otherwise implies is that everything that's unique to the mode and the measurements currently in, those settings can be found under measure setup. So please make it a point to visit that regularly to make sure that you haven't missed anything as far as the setting up of the instrument. So the available modes of the instrument, cable antenna analysis, fiber inspection, what we're going to basically, all these others that are here, what we're going to focus on today is signal analysis, LTE. Now, I do have a second LTE signal analysis session, a little bit more advanced. It will actually delve into more of the ED and some of the more advanced features of using that. But today we're going to stick with the LTE FTD as part of today's presentation. So let's start with an LTE overview. One of the most simplest block diagrams that I've seen is basically how LTE is structured. It's largely based on Ethernet connections. You can clearly see that the user plane and control plane are oftentimes divided out. But what we're going to focus on today is the UU interface. This is actually the inner interface between the base stations and the LTE mobile devices. Now, again, I don't really care whether or not it's a macro site, a micro site, a femto site, a DAS system, whatever it is. Those are just changes in power levels. The UU interface, one of my greatest fondness of it, is that it's a standard. And when I go to evaluate it, I can basically look at any one of those outputs and verify whether or not the signal quality is what I expect it to be. This table shows many of the e-ultra bands. Now, I personally tend to like to work more with frequencies because I've yet to get into a scheme where I have to memorize the channel numbers. But it's extremely important when you're communicating with people back at the switch, or if you're looking at your handset to find out where your handset is otherwise using spectrum, and you're trying to investigate problems, odds are you're going to have to use a channel number. The beauty of our instrument is you can convert or use either one, frequency or channel number, to make sure that you're within the right part of the spectrum when you're evaluating your LTE signals. In this slide, I think one of the things you may be missing, this is basically just a reference to help you understand or navigate where the spectrum is at. I highly encourage that in each one of the markets that you serve, that you have some type of a laminated cheat sheet that will quickly tell you where the centers are for your uplink and your downlink, as well as where your guard bands are and whatever you refer to your channels as far as F1, F2, again, however you communicate with others. But either way, you should be able to navigate, just like getting through the neighborhood to somebody's address. This is otherwise how you need to find your spectrum to be able to observe. One of the beauties of LTE framing is that it actually is one of the few technologies that actually has different bandwidths that can be taken advantage of. Whether it be 1.4, 3, 5, 10, 15, or 20, any one of these bandwidths are available. Notice there's a channel bandwidth as far as how the industry refers to it versus there's a transmission bandwidth, which is otherwise the actual transmission bandwidth. What this is referring to is if you look at the subcarriers, FC, you'll see the actual number of subcarriers that's in each one of those channel bandwidths. If you take these numbers times 15 kilohertz, because a subcarrier is actually 15 kilohertz wide, that is actually how you will get those transmission bandwidths at the bottom of the table. We won't spend a lot of time going into frame structure, but needless to say, basically one radio frame is 10 milliseconds. You actually have inside there 10 subframes. Each one of those subframes is divided into 2 slots. And the test instrument has the ability to park on any one of those subframes, or in fact, it can also be used to, when you say, continually rotate and monitor each subframe, which is otherwise referred to as frame testing. And you will actually see in some of the demonstrations we give how it otherwise increments through those to evaluate each one of those subframes. Now, the whole point of otherwise understanding how LTE works, you really should have a clear understanding of various modulation techniques. AM for amplitude modulation. What we're showing here is the modulated signals can be analyzed using what we refer to as polar diagrams. These are magnitude and phase, basically the in phase and the quadrature. But for amplitude, these are how the points shift. In frequency, it's basically how fast it gets back around. If you shift just the phase, this is how the points change. If you shift both the amplitude and the phase, these are how the points within the I and Q can otherwise shift. Why is this important? This is what leads us to the next slide, which is digital modulation. In the realm of binary worlds, you basically have 0 and 1, 0, 0, 0, 1, 1, 0, 1, 1. Each one of these are based upon modulation formats, whether it be BPSK, QPSK. In the world of EVDO, there's actually 8 PSK, but in the world of LTE, they use what's called ZADOP2. We're going to show you a slide a little bit later on. ZADOP2 is actually used as part of the primary synchronization signal. 16 QAM, 32 QAM is more or less just a placeholder. I have never seen 32 QAM used in a wireless world. 64 QAM. I've even seen now that there are some equipment manufacturers entertaining the aspect of doing 256 QAM over the air. 256 QAM is a valid modulation format. You generally only find that in cable TV, but believe it or not, they're actually going to attempt to put that over the air. And if you're in the right location, odds are you'll be able to use it. But when you're trying to determine the quality of that modulation at the source, error vector magnitude is the key measurement, EVM. This slide otherwise shows some of the modulation error sources. So example, on the digital to analog converter, basically you have the I and the Q. This is where you find DC offset error. Phase noise from local oscillator, quadrature skew, even gain and balance from the mixture. Now, in most cases, you probably aren't going to be troubleshooting at this level, but suffice it to say, it's oftentimes when you have a problem with error vector magnitude that if you look at the constellation, you'll oftentimes get a signature of what that problem is. I'll even describe to you a little bit later on some of those problems I've seen out in the field. So here's a slide that otherwise shows LTE downlink channels. The ones that are generally the most important are the ones that you otherwise start out with. First and foremost at the bottom of the table, it's called the reference signal. This is otherwise sometimes referred to as the pilot. We have another slide that shows you more of how this is broken down. But needless to say, the reference signal can be found throughout an LTE signal, meaning that it's used to calculate CQI, values that otherwise help the mobile tell the base station what the spectrum conditions are relative to their vantage point. Now, the primary synchronization signal and secondary synchronization signal, these two kind of can be a little confusing, because when I first learned about LTE, I came to realize that between the primary and secondary synchronization signals is how the sectors are otherwise identified. They're called PCIs. PCIs have or can have up to 514 different values. You use all of them, unlike CDMA 2000 EVDO, where you have a P in increment and you only use a fraction of the total available. In LTE, you can use all of them. Now, what confused me at first was the primary synchronization signal has 3 values. Notice it uses a modulation of Z off Q, 8 points of modulation, and only 3 values that are available to you. Secondary synchronization signal. This actually can convey up to 168 different values. What confused me was this BPSK. Wait a minute, how do we get 168 values from 2 points of modulation? I'll try to further explain that in one of later slides. But at the top here, notice the two that are a variety of different modulation formats. Again, LTE is intended to be a preemptive technology, meaning from that reference signal, it's going to tell the base station through CQI values what the RF conditions look like. If the RF conditions are really poor, the base station is going to send out the data using QPSK modulation, because 4 points of modulation is far more robust than 16 or 64 QAM. If RF conditions are ideal, it would like to use 64 QAM. And again, through the CQI values reported, this otherwise determines, as far as your vantage point, what type of throughput you can gain or receive. Now, there's also markets that's starting to use, example, Go90. LTE is a technology which actually supports multimedia broadcast of multicast service. Effectively, it's like watching TV. And they're starting to do that more and more within NFL stadiums, because they don't want everybody with their own individual user payload watching the Red Zone website. So this slide, once again, kind of shows between the different UE categories. Definitely the uplink, downlink rates have been greatly improved upon. The part of this slide that I generally refer to most is, again, this table that otherwise shows, again, the channel bandwidth, transmission bandwidth, more importantly, how many resource blocks and subcarriers actually can be found within each one of the respective channel types. This slide is trying to get you from a real world into a understanding of signals. These 2 blue line displays are actual real displays that you can get from our test instrument. The upper left-hand corner is actually a spectrum analyzer that uses frequency versus amplitude. And you can see the breakdown of this, basically where you would have a 10 megahertz channel width, that would actually break down into 600 subcarriers. Here we're just showing a small fraction of them, about a dozen of those subcarriers. So it's just a small part of the 600 that are available to you. This middle blue line on the top is actually what's oftentimes referred to as a zero span on a spectrum analyzer. Zero span meaning that all it shows you is the amplitude over time relative to a specific frequency. In this case, it looks very much like a idle channel. These little spikes that are throughout most of this, throughout the frame, are the reference signals. Whereas the open areas that you see at slot or subframe 0 and subframe 5 are actually the primary secondary sync found in both these locations, as well as a broadcast channel. But the point of this slide is to actually help you understand that these 15 kilohertz signals, when looked at over time, otherwise creates this bird's eye view of a resource block. These resource blocks are oftentimes how the spectrum is allocated, as well as time slots for the various subframes, to the subscriber units. This slide we oftentimes affectionately refer to as the carpet or the rug. This is probably the one slide that helped me to fully come to appreciate the structure of an LTE signal. Now, if you note, each one of these little square boxes are actually subcarriers, or 15 kilohertz wide. If you took the time to count each one of these blocks, you'll find there's about 80 of these from the top to the bottom. So this is basically just a fraction of the 600 that you would find on a 10 megahertz channel. But what's important to note is that this is where you will find most of the control channels is down the center of a downlink LTE signal. The light blue and the dark blue from the primary and the secondary sync. Remember I said the secondary sync, now sometimes you'll see it referred to as a channel. I personally don't refer to it as a channel because the information is static. It does not change. To me, it's more of a signal. But what's more important is to realize that the secondary sync has multiple ones and zeros. So that BPSK, each one of these blocks is going to be either a 1 or a 0. That's how we ultimately got that 168 different values. And the primary synchronization, that light blue, even though there's only 3 values, each one of these points is 8 points of modulation, that's 8 off 2, which further emphasizes why that's used as the primary synchronization for understanding the different modulations. That is, in fact, the primary reference. Now notice the red highlighted areas. This is actually the resource blocks, and those are otherwise found throughout time as well as across lowest to highest frequencies, and actually reminded me of a movie. Some of you may be able to guess what that movie is. It's actually The Matrix. They're sitting in front of a terminal. People are watching the characters as they fall down the screen, and they can otherwise make up images of where people are at, where they're doing, where they should go. Effectively, welcome to LTE. We're getting barraged over the air with a variety of different symbols that otherwise can represent audio, video, data, voice, any one of a number of combinations which otherwise makes up the content for what you're seeing coming across your user device. This slide clearly helped put things together. When I first heard of MIMO, where they said we can use 2 transmits with 2 different data streams, doubling the effective capacity or throughput of the data pipe that we're sending, I was very confused as to, okay, how do the receives otherwise differentiate between the 2 different transmits? Sometimes it's referred to RS0 and RS1. And what I came to realize or appreciate is that in the first transmit, it occupies half of those reference signals. Those little yellow squares we saw within the carpet rug on this previous slide, it occupies half of those. That's how you basically identify or differentiate between transmit 0 and transmit 1. Now, eventually, you're going to see 4x4 MIMO. In that case, what will happen is each one of these transmits will occupy 1 reference signal. Thus, the receives will be able to otherwise differentiate between transmits and be able to realize each one of those individual data streams. Again, what's important for identifying the different transmits is each one occupies a different part of the receive. Now, I do want to share something with you. Example, of Alcatel-Lucent. In 3GPP specifications, remember we talked about the primary, secondary sync? These are what's used to identify a sector. And 3GPP specifications allows or requires that it be on at least the first transmit, but it's optional as to whether or not they put on the second transmit. In most cases, equipment manufacturers put primary, secondary sync on both of them. Alcatel-Lucent chose to only put it on the first. So beware that when you're looking at the second transmit from an Alcatel-Lucent, you actually have to go into the measure setup and manually set the PCI to match that transmit, meaning match the transmit you'd otherwise got from the first one. Otherwise, you will not be able to see the characteristics of that second transmit for ALU unless you manually identify what is the PCI value, because they don't put primary, secondary sync on the second transmit for ALU infrastructure. Keep that in mind. I was actually in Puerto Rico. They had a mall that they couldn't get the LTE to work because they were using an existing DAS system, and they came to find out, or I came to point out to them, that they had dummied off the first transmit, which means that they were transmitting into the mall the second transmit with no identity. And all they had to do was swap the cables, and in 30 minutes we had the problem fixed, and they'd been spending weeks trying to figure out what was wrong. So great use of signal analysis. All right, this slide is otherwise trying to show, again, that reference signal. It plays a very important role that through that reference signal, the handset is going to use that channel state information and actually create a channel quality indicator. CQI, as it's otherwise known, is a value from 0 to 15. If you're using 1 to 6 or the phone reports 1 to 6, as a preemptive technology, the scheduler is going to, odds are, send it out as a QPSK to otherwise try to get it right the first time. If the CQI value comes back from 10 to 15, then it will otherwise try to use 64 QAM to get as much data content. Conditions are ideal. That's part of what this slide is always trying to convey. other modulation formats will you otherwise be receiving. Now, RF signal quality of the end user or system capacity. What you need to bear in mind is that when a signal leaves a transmitter, it's not going to get any better as it goes through the air. Now, in 3GPP specifications, even when UMTS first came out, they referred to something known as beam forming, meaning in an ideal world they'd like to direct the RF energy only to the people who otherwise need it. So, DAS systems oftentimes will have that first opportunity to create small RF patterns where people tend to congregate. So again, RF coverage patterns, you're trying to follow where subscribers are, trying to get that RF off the air as quickly as possible, getting it onto a piece of wire, meaning where the antenna is at. By placing multiple antennas close to the end users, you create smaller footprints, but realize that the best coverage is where you minimize the overlap between adjacent sites and sectors. If you have too much overlap, it's kind of like having too many speakers at one time, meaning that if you added 2 or 3 other people to the same webinar, it'd be very difficult to basically follow each one of us. Receivers are no different. They work better when you have pilot dominance, meaning a single sector serving you, and you have minimal overlap between those various sites and sectors. So bear that in mind, but also bear this in mind. DAS systems have been phenomenal about creating higher capacity in large venues or in buildings or where people tend to congregate. But DAS systems have 2 very important purposes in life. One is to get signal quality from point A, meaning the BTS, out to these antennas without degrading that signal quality, as well as get signals from the input into those radios at the remotes back to the BTS without degrading the signal quality. A lot of this comes down to dynamic range, meaning you've left enough headroom and you're not overdriving or underdriving any one of these components. We actually have a DAS comparison test that will allow you to measure the output of the signal from the BTS and then determine how well the DAS system has maintained that signal quality out to the ends. The second role or purpose of a DAS system is to, again, have antennas that are otherwise, to have these antennas placed where they don't compete with each other and they don't compete with the macro sites. Again, a DAS system ideally is trying to fill coverage holes, but if you're trying to deploy a DAS system, the macro site should be adjusted accordingly so that they're not competing with each other. Either that or antennas need to be placed where they're not otherwise providing disruption in that signal quality. Now this is basically dating back to the original Alcatel-Lucent eNodeBs, the TRDUs. I have great admiration for them because they actually provided not only the receive test points to look at uplink interference and issues potentially with them, but they also provide transmit test points. These actually use a test connector known as a 1.0/2.3. When I first saw them, and I've seen many people, veterans, refer to these as SMBs. They are not. They look very similar to SMBs, but the diameters are different. Again, they're 1.0/2.3, 50 ohm. There's also the same thing, 1.0/2.3, 75 ohm, but the ones that they use are 1.0/2.3, 50 ohm. These are 40 dB down test points. Now, this helps protect the instrument using these test points when you're otherwise looking at the signal quality out of these transmitters. But even with these attenuated test points, you still oftentimes need in the order of about 25 to 30 dB of internal attenuation as part of the test set to not distort that signal. I can get 4 error vector magnitude from my instrument if I'm overdriving it. So please add that extra attenuation. On Ericsson, the eNodeBs did not have any transmit test points. Some service providers actually add and want to ensure that they have those transmit test points that are already pre-installed so they're not disrupting service. The pass-through loss of these are extremely low, but this again is a 40 dB down test point, uses a QMA connector, and be careful of these right angle connectors. Anytime you're talking about a right angle connector, I strongly suggest that you make that threaded connection on the right angle before you thread on the top connector. We have heard from accounts that when people otherwise make this connection first and they tighten it down, not a lot of undue pressure and oftentimes damages the center pin of those cables because of the mating and now torquing of that connector. So please make sure you connect the right angle before you connect up the top part of the connector. But again, as far as efficiency and false isolation, this is an excellent test point to otherwise increase your efficiency without disrupting customers' experience when you're trying to evaluate signal quality coming out of your transmitters. Now, considerations before you start. LTE customers do expect higher throughputs everywhere. And odds are the 3G coverage is better because the technology doesn't support quite as high of coverage. But again, the 3G, 4G, in both cases, they should complement and not compete with existing coverage. When it's a frequency reuse of one, pilot dominance, meaning minimal overlap between sites and sectors, is your friend. That is where you're going to get the higher modulation rates. Also note that during major gatherings of crowd movement, oftentimes it's very beneficial to dynamically change RF coverage. Example of a stadium where you may have macro sites covering the parking lot during the tailgating experience at game time. You oftentimes want to turn down those macros so that the DAS system can otherwise now take full advantage of the spectrum and to serve the people within inside the stadium. So bear that in mind. But again, in any system, you basically have licensees that must approve reuse, or when you say retransmitting their spectrum. This slide is to further convey or reinforce that what happens with when PCIs, again, this identity of each one of those LTE sectors, are within 5 dB of the dominant sector or the dominant server. This is titled the RF waste trap. As you can see by these little sidearm triangles or the diamond that are shown here, anytime you have a second sector trying to serve you, meaning within 5 dB of the first, it greatly degrades the signal quality. Signal values considerably drop considerably. It's not ideal coverage. So if you hear the commercial more bars, more places, if you're close to an antenna, great. But if it's because they simply turn up the power, that's not a, good RF approach, maybe a great marketing approach, but from an engineering standpoint, 3G and 4G technologies, you're trying to maximize your RF usage by minimizing the overlap. Now we're going to delve into a little bit of the hands-on. I'm going to share with you some of the slides that we have for the various measurements that we support, but I'll also actually use the instrument itself and walk you through, and you can see some of the spectrum here at my home in the Chicagoland area. How we organize LTE signal analysis measurements is actually into 3 main groups. RF analysis. The brunt of RF analysis are spectrum analyzer type of displays, where you can get channel power, occupied bandwidth, spectrum emission mass, adjacent channel power, leakage ratio, spurious emissions. Many and most of these are actually spectrum analyzer type measurements. These are generally for qualifying a transmitter as to whether or not it meets industry standards. My personal favorite is all the way over here on the right-hand side, the over-the-air analysis. Now, don't be misled. You can do over-the-air analysis measurement as well as modulation analysis measurements, which are primarily intended for hardware connection over the air and vice versa. My favorite is basically the ID scanner, because when I'm basically making a measurement, especially on the DAS system or over the air, immediately I want to determine how many sectors are trying to serve me. And can I get ideal RF conditions that make it look like I have what is almost as good as a hardwired connection. The ID scanner is going to tell me how many sectors are otherwise trying to serve me, as well as its dominance and signer values, multipath profile, and actually it's probably a good time to actually switch over to show you some of what I can share of my over-the-air measurements. Now how I got here was, again, I'm already in the LTE FDD mode, so I'm not going to waste time by reloading it, but if I go to the measure, you'll find here's the modulation analysis. Notice the little, there's the RF analysis. And the auto measure is actually a collection of many of the modulation analysis where we'll run through and do a whole series of tests. And even the DAS comparison test is to be found on the auto measure. But the one I generally gravitate first and foremost, in almost 90-95% of what I'm looking at, is the more one of two, the over the group. Again, notice the black icon, because that otherwise shows that it has multiple measures underneath. And here's my ID scanner. You can see I've already got the ID scanner selected. And here's what I'm looking at. 866.3 is actually, one of Sprint's LTE 5 megahertz downlink channels. And what's most important to me is the right-hand dB scale. The dBm scale is a raw signal strength of both the reference signal as well as the secondary sync. RSSI, it has very little to do with your signal quality and what type of data rate you're going to get. However, on the right-hand side, this violet bar here, well, first of all, notice the 253s that are actually very static. That means one sector. This is clearly an LTE signal, and I've locked onto it. But I look at two columns. I look at the SINAR. Notice these high 2932s. This is a very good SINAR value. The full scale, and what I expect to see through a hardwired connection, is actually 40. But high 20s, low 30s, over the air, this is actually considered pretty good. Notice the far right part of this table. This is that dominance, or otherwise the height of that secondary sync, and whether or not there's any other sectors being seen or competing with that secondary sync. In this case, it's very good coverage. Now, let me go ahead and quickly change over to a couple other carriers. I'm going to change the center frequency to 751 megahertz, which is Verizon's LTE downlink at 700. Now, I do need to go to the measure setup and choose the respective bandwidth of 10 megahertz to properly characterize this. And here you can see SINAR values actually in the mid-20s, actually pretty good, 220, 221, adjacent sectors. You can clearly see that I'm actually splitting between two sectors more often at AT&T. I'm going to put in a center frequency of 739. They too are a 10 megahertz wide carrier here in the Chicagoland area. And let's see how well they serve me here at my home. Here we can see 330 and 331 are the primary two, but notice our SINARs are considerably lower. I may be actually splitting or a little bit, on the Verizon, I hedge towards one sector. Well, for AT&T, where this antenna is, located right now, looks like it's right in the middle of the two. So that's not ideal RF conditions for getting the highest possible modulation rates. So again, I wanted to share that with you before I move on. Again, all these measurements and the analyses performed over the air, but again, we actually organized them originally because the primary role is to a hardwired connection. But I tend to use over-the-air analysis because it provides me probably close to 90% of what I need to know in terms of RF conditions, whether it be through the ID scanner or the multipath, and even the control channels. And we'll share some more slides with that. Here's basically some hands-on how I got there. Again, measure over-the-air ID scanner, or for multipath profile, measure over-the-air multipath profile. The big advantage of multipath profile is I can clearly see MIMO. If I have these peaks here at the top, I can clearly see that, yes, I have both transmits. I can even go so far. Let's go ahead and choose the over-the-air, and I'm going to change the measure setup. And let me actually go to my measure, get myself there a little faster. More 102, OTA, multipath profile. As you start deploying or hearing about 4x4 MIMO, if you go to the measure setup, in fact, most of these measures have a miscellaneous. On the measure setup miscellaneous, if I go to this, you'll see that I can actually switch it from 2x2 to 4x4 MIMO. And it will actually display that, yes, I have two transit paths on the antenna 0 and antenna 1. Notice the use of CI0, low values in the first half, but on the 2 and 3, I don't have anything. So obviously I do not have 4x4 MIMO on AT&T's network, but this is one way of quickly verifying what do I have in way of MIMO. The tool for quickly identifying whether or not you have MIMO. These are some of the more advanced. You can actually set up the instrument to look at carrier aggregation, where you're actually looking at up to 5 different LTE carriers at the same time. They can be of different bandwidths, but you can quickly determine whether or not you're seeing, if you have a 4x4 MIMO, whether or not you have all 4 of them being received. You can place the marker and actually see the modulation quality of the various signals. Again, trying to assess what is the signal quality. In fact, I'm going to share with you an analogy. When it comes to spectrum analysis, to me, that's like driving through a neighborhood, whether it's residential, commercial, industrial. I can generally tell you what kind of neighborhood it is by driving down the street, in this case, spectrum analysis, to look at the spectral content and whether or not everybody's where they're supposed to be and if there's anything out of place as far as the neighborhood. When it comes to signal analysis, I effectively think of this as walking into somebody's home or place of business and telling them whether or not their house is in order. Trust me, I have seen numerous clues or indications of functional or performance issues that people were totally unaware of until you actually provide them visibility using signal analysis. Now, on the control channel, the greatest use of it is to actually look at the polarity of the two antennas. Example, transmit 0, transmit 1, oftentimes are plus 45, minus 45. And what you can do with this, if you have an antenna, as you rotate it 90 degrees, you should be able to see that the amplitude changes position as to who's stronger. There was one class I was giving inside the room and saw an 11 dB difference. In fact, you'll notice on this table, note the reference signal 0. On this second column, this 0 value for reference signal 0. This is the reference that everything else is measured by, and I actually in this classroom had seen an 11 dB difference between RS0 and RS1. I was astounded. First time I'd seen 11 dB difference between the two transmits. I rotated my antenna, and it didn't change. Now I'm really pondering what's going on here, and we came to realize that we were part of a repeater. So the donor antenna that was actually mounted on top of the roof was giving both directional and polarity preference to the first transmit. It was effectively ignoring the second transmit by a factor of 11 dB. So if you basically know signal analysis, you can otherwise determine are the various transmit paths. In this case, on a repeater, it was not good at all. Here's the ID scanner. Again, just a slide that otherwise shows detecting multiple cell IDs. And again, RF conditions are ideal when you have a single one with lots of dominance and a very high SINAR value. The multipath we talked about, control channel we also talked about. Now, bear something else in mind. Notice that at the top of this display, you'll see a latitude, longitude, but more importantly, that green icon. This tells me that they had a GPS antenna connected to the instrument when they're making the connection, and the frequency error is probably going to be with that's what we see. Now, there can also be another problem with MIMO, and that is the time alignment, meaning the timing difference between the two transmits, otherwise referred to as reference signal 0 and reference signal 1. This can oftentimes happen on DAS systems where they use cable links that are varying different lengths, whether it be fiber or RF cables. If it's greater than 65 nanoseconds, then you will probably have a problem with your handsets being able to take advantage. So a great display to otherwise also ensure the signal quality, what you've got going on, and how good the end experience is going to be of the user. That's one that I actually used very extensively when I first started evaluating LTE because there's no traffic out there. There is the control channels. Notice the subframe 0. You can actually set the measures work on any one of the 10 subframes that LTE offers. Subframe 0 has more information because it has a primary secondary sync in it as well as a broadcast. Notice the reference signal here, and that's the one highlighted. By using the markers and moving the markers around, you can actually see the constellation for each one of these. I will share with you an experience where I was at MetLife Stadium and asked the service provider where they're having performance problems. At first, they were thinking I was getting all up in their business, but I explained to them that I felt that they probably knew where all their functional problems, but one of the best benefits that we could offer with this instrument was to investigate performance issues. Well, they actually came to realize that, yes, I could probably help them in an area that they've otherwise not been able to solve, and they commented that on the third level concourse, they had sectors that never performed as well as the other sectors within the stadium, whether it be from walking the stadium and doing speed tests, or when monitoring from the core, these sectors never asked. Then asked them to do was to take me to a good sector. Now, to take me to a good sector, I'm served by investing time looking at known good signals. That's because when you're investigating a problem, it will be more obvious what is exactly out of place. So I took them to a good sector to show them the SINAR values, the dominance, and what I was able to do by pointing a directional antenna right at the known good sector. I then asked them to take me to the worst performing sector, and in fact, sure enough, the SINAR values were not good, error vector magnitude values were not good. What we came to realize was that when both antenna elements were transmitting, instead of getting 4 points of QPSK, these 4 little dots, we had 4 perfect circles. But it was only when both transmit antennas were transmitting. We'd gone to hardwired connections at the DAS system as well as on the output of the radio, and both transmit signals were perfect. We actually turned off one transmit, letting the other one on, and the signal was perfect. We alternated. We swapped which one was transmitting. Each one individually, the signals were perfect. Unfortunately, the physical spacing between these antenna elements, because they were inside of an enclosure, when they were both transmitting, was actually degrading the modulation quality. So we had actually isolated the failure to an antenna enclosure through signal analysis and using our instrument. So bear that in mind. If you do get a higher than expected intervector magnitude value, and you have otherwise what would be considered ideal RF conditions, because you're hardwired into it or you're created pilot dominance and minimal multipath power, this is what the constellation or the values of the intervector magnitude should be approaching. Again, this is probably a hardwired connection because these values are actually quite low, meaning very, very good. Now, the data channel is another display that I'm very fond of, but unfortunately, it's only as valuable as the ability to control your transmitter, meaning the output. If you're using OCNS, AILG test modes, you may be able to actually identify what modulation will be used in each one of those various resource blocks. In our CPRI interface, we can actually do signal generation and actually now provide a fixed reference to determine whether it's at the lowest frequency or the highest frequency, whether or not it's maintained signal quality for a specific pattern. But this is a perfect example of testability and the ability to control the output of your own transmitter. Data Allocation Map, yet another display that can otherwise help you determine what type of user traffic is present for that LTE carrier. Now this is one of those measurements. You'll notice the little white square right here. It will continue to rotate around and around, showing you what's taking place in way of traffic. Over here at Modulation Analysis, again, I'm doing this over the air. It's generally preferred for this group to be done through a hardwired connection, or at least have better pilot dominance. But this can oftentimes be used to help me determine what type of traffic loading are seen on each one of these various carriers. I'm going to change this over back to Verizon, because right now I'm not seeing a whole lot of traffic. There we go. See that block of traffic? That's actually, here's another small block of traffic. There's a large block of traffic. There we just saw, let me say, Verizon at this particular point in time, at this particular location, data allocation map, shows that they're actually experiencing a higher usage, at least at this point in the spectrum. And again, they have other things they can do to offload to the PCS, AWS bands. But again, this is a great display to otherwise determine what type of loading you're otherwise seeing on that sector. Frame summary is very similar to data allocation. When you have this measurement up, you'll actually watch the subframe will count up and the table will get updated relative to which subframe it's evaluating. Notice the area highlighted here. This is for the actual user, QPSK 16 QAM or 64 QAM in use. And again, very useful, but what I want to share with you is that be careful. When you're looking at a manufacturer failing 64 QAM because their modulation to a hardwired connection was actually exceeding 8%. There's other thresholds for 3GPP as far as what they'll tolerate, but in most cases, the smaller this number, better throughput and capacity on your network. On the subframe, very, very similar, and we'll continually monitor that subframe for signal quality. And again, you can see maybe there's a zero span. Channel power, again, the traditional way of using a spectrum analyzer to look at channel power. Don't use this very often, but again, if you're evaluating a transmitter, plus or minus 2.5 dB. LTE is very tolerant as far as the specification of how much power you can actually have. Now, if it's looking at live traffic, this plus or minus is going to be much, 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 much bigger. Generally through OCNS, AILG test modes that you'd otherwise have live traffic, it's not going to be stable. It's going to be all over the place. Occupied bandwidth, again, we're just going to kind of skip through these very quickly. Adjacent channel leakage ratio, age-old way of evaluating a transmitter to make sure it doesn't have any problems with interfering with adjacent spectrum. Spurious emissions, as you can see by the table, it's actually looking all the way across the spectrum from 100 kilohertz all the way up to 7.2 gigahertz in various chunks, looking to make sure that your transmitter doesn't otherwise have spurious emissions into spectrum that it should not be trespassing on. Notice our spectrum emission mask. The spectrum emissions mask is a point segment line, the slight slope on the area of the shoulders. I can tell you quite clearly that when you see a spectrum analyzer on a signal that has very clear slopes on the side or shoulders going up, odds are you're overdriving the instrument. In this case, you have about 15 dB of internal attenuation, and the slopes are really not that bad. They kind of mimic the multi-segment line. But if you overdrive our instrument, odds are you're going to have bad error vector magnitude values, bad SINR values. But again, it's because you didn't adjust the signal to a dynamic range that the instrument otherwise wants to measure that. You'll often in the lower left-hand corner when you have otherwise exceeded that. Here's the MIMO time alignment error. Again, ideally you'd like to use a divider combiner to do that. It should be less than 65 nanoseconds. If it's greater than that, odds are you're not going to be able to take advantage of MIMO. It's complementary cumulative distribution function. This, as I understand, is an excellent way to understand the performance or the probability over time as far as the behavior of a transmitter and the linearity of the amplifiers. But it's generally done more in a manufacturing or a engineering environment where you're designing it. Not very often do I see this test in the field. But again, if you have a transmitter that's in question, it may be a test you might want to run. This is the automated testing where we otherwise combine, whether it be RF analysis, modulation analysis, or power versus time. And you can actually generally do this through a hardwired connection, plug it in, give it the center frequency, and tell it what test you want to run and what the limits are, and it will run through the whole series, and at the end you get a pass or fail. Again, this is one way of evaluating very comprehensively many of the different performance characteristics and signal qualities of your transmitter. That concludes our slides.